Alright, dear children of class 11 science, now we do again a topic based on displacement equation in terms of initial phase. Now initial phase is also called epoch under simple harmonic motion. So in the last YouTube videos you saw we measured even the displacement, velocity, acceleration, okay, in terms of simple harmonic motion, okay, by considering that the particle displaced from the reference line, that is called origin, okay, also called equilibrium position, okay. But the displacement equation can be even written in terms of initial phase or epoch under simple harmonic motion. This means, now in order to write the displacement equation in terms of this epoch, okay, or initial phase, so let's try to understand what is phase. So let's try to understand what is phase. So this is one of the important term in simple harmonic motion. Now when a particle oscillates, children, when a particle oscillates in simple harmonic motion, its position and direction of motion varies with time. So position and the direction of motion when the particle oscillates in simple harmonic motion varies with time. It changes with time. Now the phase of a vibrating particle, at any instant actually expresses the position and the direction of motion of the particle at any instant of time. Which means phase of a particle can be defined as it is the phase of a vibrating particle at any instant of time express the position of that particle and even the direction of motion of the particle at that instant of time. So phase indicate the position of the particle and even it indicates the direction of motion of the particle. Okay, so this is the term that we can define phase. And phase is basically expressed in terms of angle. So it is expressed in terms of angle. It is expressed. Okay, let me just write down. It is expressed in terms of angle. In terms of angle. And we mark angle by phi. So no problem. We can use the symbol like phi as the symbol we use for phase of a particle at any time. Okay, but sometimes it can be expressed in terms of time period also. Okay, it can be expressed in terms of time period also. Now in order to write the displacement equation in terms of this phase, which is also called initial phase, also called epoch, okay, so let me take this diagram. This is a circle, okay, because we know simple harmonic motion is always expressed as a projection of uniform circular motion. So again I am taking this circle, okay, having diameters on y-axis, the diameter on y-axis. Let me just give the name as say b dash, and this is the diameter along which axis, x-axis, and we give the name as say a dash. Okay, now these two diameters intersect each other at this point, so let me mark this point as O. Okay, so this point is O. Now in order to express this displacement in terms of initial phase, we know this line is a reference line and we consider this line as an equilibrium or mean position line when the particle executes simple harmonic motion. Okay, but out here, in order to write this displacement in terms of initial phase, I consider that the particle is starting its motion, but the particle is starting its motion other than this reference line, say at a point this. So let me just mark this point, say at A1. So A1 is the position, the initial position of particle where the particle in a simple harmonic motion execute in a simple harmonic motion it echo the motion. Okay, that means this particle is already at point A1 of this reference line. So which means with this reference line the particle has already make initial position, and this initial position is expressed by initial phase. And let me now mark by symbol phi. So as I said already, the phi is the symbol we use for phase. Okay, so this is the position, initial position occurred by the particle before it start the motion. So with respect to this line, so this particle makes certain angle with the reference line, and that angle is phi, and this angle phi indicate the initial phase. This is phase? Initial phase, also called epoch. So as for the diagram, if you see, now this position of the particle with the reference line makes angle, that is phi, and this angle we mark by letter angle A1OA, and this angle is phi. So A1OA is the angle, initial phase angle, okay, and that is called epoch, and that is given by phi. Now after that the particle will displace, okay, other than this point A and reach to some of the points say P. Suppose the particle reaches to this point say P at after a certain time interval say T. So when a particle displaces from this point A1 to P after a certain time interval T, okay, then there is an angular displacement of the particle, displaced particle from A1 to P, and that angular displacement I consider as omega T. What is the angular displacement? Omega T. But this position of particle with respect to center is equal to the radius of the circle, and we will take the radius of the circle as what? A. So A is the radius of the circle. Okay, so out here you can see A, again we use the symbol as the radius of a circle. But children, you know this radius of circle is equals also to the what? Amplitude. The amplitude of the what? Simple harmonic motion. Amplitude of what motion? Simple harmonic motion. Okay, now if you look at this diagram, okay, particle is at point P at any certain time after moving from A1. So mean the angular displacement omega T. That means angular displacement omega T is expressed by also what? Theta. And theta is also called what displacement? Angular what? Displacement. Angular what? Displacement. Then in order to calculate the displacement of the particle of P from this reference line, also called equilibrium position, is calculated by drawing a perpendicular line along this axis, along this diameter, and that is represented by, let me mark this person N, and this is given by what? Y. So ON, if you see in the diagram, is Y, and this Y give you the what? Displacement. This measure the displacement, okay, of a particle. This measure the displacement of particle, okay, from the what position? From the equilibrium position. From the equilibrium position. Now equilibrium position means with respect to what line? The reference line. Okay, with respect to reference line after a time interval. After, okay, let me write down after time interval, and that time interval I write down as what? T. Okay, now this ON now can be easily calculated in terms of what? This right angle triangle. Now for that, if you look at the diagram, the angle made by this point P, the position of particle after time T, with reference to this equilibrium position, also called reference line, will be given by angle POA, and this POA is given by phi plus omega T. See, this angle plus this angle give you the total angle. This is the total angle. That means POA, angle POA equals to phi plus omega T. I mean, this angle is phi plus omega T. Now, if you look at this diagram, children, there is a right angle triangle formed by the displacement particle with the equilibrium line, which means you can see the diagram like this. This is a right angle triangle which is formed. This is P, this is N, this is what? O. And this displacement need to calculate. Now this displacement, this is a displacement, this is the amplitude which is equal to radius. Okay. Now in this, you can see this angle is, this whole angle is how much? Phi plus omega T. If this angle is phi plus omega T, then this angle is also how much? Phi plus omega T. So children, look at this. This angle in this right angle triangle is also phi plus omega T. Now why? Because the two angles are alternate angles. Because the two lines are parallel. When two lines are parallel and one line is at a transversal line, the alternate angles are equal. Okay. Now from this right angle triangle, we calculate this displacement. Because in this right angle triangle, the displacement in this right angle triangle with this angle phi plus omega T, this side is your perpendicular. This is your perpendicular. This is your what? Hypotenuse. And we know we need to express perpendicular in terms of hypotenuse. And you know perpendicular and hypotenuse are related by what? Sine. So I follow that in right angle triangle. Okay, right angle triangle O and P. Let me mark this clearly. O and P is a right angle triangle. ON is your Y, and you know this is your perpendicular. This is your what? Perpendicular. And you can see OP. Yes, OP equals to A, and this is your what? Hypotenuse. So if perpendicular is to be expressed in terms of hypotenuse, means we follow what? Which trigonometry? Sine. Some people have, because we know sine of phi. Now angle is how much? Angle is what? Phi plus omega T equals to perpendicular by hypotenuse. See, P by H. But what is perpendicular? ON. So what is the hypotenuse? OP. Now if you do cross multiply, we can write now this as ON equals to OP sine phi plus omega t. So ON equals OP sine phi plus omega t. Okay. Now OP means what? A. Now let me substitute. OP means what? A. OP means A. And this is sine phi plus what? Omega t. So now see ON actually means what? Y. So Y is the displacement which goes to A sine phi plus omega t. So look at the relation that we derived now. This is the displacement equation, and the displacement equation in simple harmonic motion in terms of epoch or initial phase is given by Y equals to A sine phi plus omega t. Now the same relation now we can write even as Y equals to A sine omega t plus what? Phi. Same thing. Okay. So this is the displacement equation of simple harmonic motion. Okay. In terms of what? Epoch or the initial phase. Okay. Thus, at any instant of time, the phase of n will be measured in terms of total angle. So this is the total angle, where phi is called what? As I said, phi is called initial phase. This is the initial phase, or we also call epoch, and we use this formula in solving numerical problem also. But this is the general equation of simple harmonic motion in terms of what? Initial phase or epoch. When the particle is starting other than the reference line, on the which side? Positive side. But it can be the case where the particle may start other than the reference line from the negative side also. I mean to say, the particle may start from the other than the reference line but below the reference line. So same diagram, but this is the reference line, that is called equilibrium position, and the particle starting from A1, which is lying at an angle phi minus phi with reference to reference line, because when you move this side the angle will be negative, means the position occurred by the particle with reference to reference line will be expressed by minus phi, and this minus phi is also the initial phase. So when the particle starts from this point A1 and acquire a position say P after a time interval t, then with respect to this point, this distance will be a only. This distance will be a only, and with respect to this reference line, the point where the particle is caught, the angular displacement will be omega t. See, the angular displacement measured from the point where the particle starts its motion. Motion starting from A1 and reach to P. So this omega t is the angular displacement. So omega t is the angular displacement, and this angle is initial phase. But we need to calculate this angle, the angle which we measure with reference to reference line. Now this angle now it will be called omega t minus phi. Omega t minus phi measure this angle, that is omega t minus phi. So that means this is the angle, okay, angular displacement of the particle with reference to the reference line or from equilibrium position. So under this case also, if I drop a perpendicular line on this y-axis with n, we measure the displacement, and that displacement is again what? Y. But under this case situation, your displacement equation is simply given by a, look at it, a sine omega t minus phi. So look at it. The displacement equation can be like this also. The displacement equation can be written as y equals to a sine omega t minus phi. But this equation is true when the particle starts from this position, and this equation is true when the particle starts from other position above the reference line. So children, simple harmonic motion express the different equation, but one of the equation which express simple harmonic motion is the displacement equation, and this displacement equation we have expressed just now in terms of epoch or initial phase. So in this relation, the epoch or initial phase is positive. In this case, the epoch which is what? Negative. Okay. So with this relation, we do some numericals also. Okay. Now in the next YouTube video, we discuss in detail about the fourth law for simple harmonic motion, and with that we derive the expression of time period of simple harmonic motion.